Uh, the last lecture was about trees. And I finished talking about this example. So the example where we have a sentence and we want to arrange all these words in form of the tree, which is used to sort or to order these words alphabetically, and moreover to count the number of the frequency of particular particular word. So I showed you how to create this tree, let's say manually. In a moment, I will show you how to implement it in code. But now I'd like to tell you how we can move inside tree. So talking about trees, we have oops. Something is wrong. You know that all elements are ordered. So the smallest element, so this element smallest in alphabetic order, is the most left one. So we have to select always the left edge. Okay, and the largest element is the most right one. So we have always to select the right edge. So now the smallest is A and the largest is 2. So now I'd like to tell you how we can move inside tree and how to visit all elements. So look, we have function which is a recursive function. So we have print element. So element is the node type. And now inside this function, we call again print left element. So the element on the left subtree. Then print current element and print right element. So now let's try to analyze how it works. So I have, oops. Oops, so something is wrong with my tablet. Oops. Okay, I have to verify it later. So look, let's assume that I call the print root first. So when I call p root, then inside this function, the print left element is called. So I have a recursive call print. So the b, okay, it's not a b literally because it's a node, but I write it, symbolically that print b is called. Then when I am here, again, I have print l. So I call print a here. And now when I am inside the printing this element, so there are no left subtree. So this function is not executed, and I have cout element. So now on the screen A is printed. Then I have print write elements. There are no write elements, so nothing is printed. So this function is finished. So now I am my program returns to print B. So the print left subtree has been already executed. So I have print cout. So B is printed. And now print R. So it calls print or. And again, if I have print or, the print left subtree is executed, so print not, and again print is. So is will be printed, then not will be printed, then or will be printed, then write subtree, so print this, but before a question. So I have question here, then this. There are no write subtrees, so this function is terminated, or function is terminated. B is terminated, so I go to the 2, so the left subtree was fully printed, so now I print 2. So look, I have A, B is not, or question this, so 2. So you can see that these words are arranged alphabetically. So this is the way how we can move from the one node of the tree to another node in the order, in proper order. Okay, so there are nothing here because this appeared, but I hope you could see how I can move through, so how I can visit all elements in the tree in proper order. Yeah. So now I'd like to show you how to create a tree and how to read and display statistics, statistic for some text. Okay, so okay, so I'd like to do it from scratch. So first, I have to define a structure element which is able to be a node of the tree. So I create structure node, and the node consists of several things. So the first is car word. So let's say that there are no word which is bigger than 25 characters. int. So I calculate, so here I have the variable which will be incremented every time when the word will be found. So this is a simple counter. And now to create element which is able to be a node of a tree, I have to define two pointers. So node pointer to left. So let's say left subtree, and node pointer to right subtree. Okay. Now I have to create a new maybe not yet. Okay, so let's assume that I'd like to read the first word. So maybe here. Okay. So look. Not. Okay. So look, here I have a file. This is a license. And now I'd like to make statistics for this file. So I'd like to print all unique words which are here, and to count how many words. So to count a frequency for every word. So to do it, I will be talking about files later on, but now I will show you how to read this file word by word. So I use something which is called fstream. I create Okay, so here is a very simple program which reads this file word by word. So if I create a stream, it behaves similar to the cin object. So now I, from not cin, but from str, so the source of str is the license file, I read a single word and then I print it. Of course, to do it, I have to write do while, oops. Okay, so I have a loop which is executed as long as the end of file is not found. So this function let's to determine whether we reach the end of license file. So running this code, oops. Okay, my misprint. Yeah. So look, running this code, you can see that every word was, so word, I mean the string of character splitted by space. Yeah, so you can see that the words are software with a colon and yeah, but you can see that this file was splitted into words. So when I try to get to the end, you can see that the last word is software. So yeah, so here you can see that the software is the last word. There is something with stack smashing, so it may be a symptom that 25 characters is not enough. So maybe somewhere there are words which are bigger. So let's assume that I use not 25, but 100. Okay, so now there are no info that a stack smashing problem occurred. Okay, so look, now I have code which extracts words from text. And now I'd like to organize these words in a form of binary tree. So let's assume the first issue. For binary tree, I need to have a root element. So initially the root element is null pointer, so it's 0. Yeah, so there are no elements in a tree. So if it is true, so if root is equal to null pointer, then I have to insert the first element in the tree. So how to do it? Okay, I can, for example, allocate memory for a new node. And now, instead of writing element to array of words, I can write this element directly to TMP word. Oops. Because this is the only element in the tree, the TMP left subtree should be null pointer, and the same tmp right sub3 should be also a null pointer. Okay. So this is the way how I can create a single element on a list. But if not, so if it is not the first element, okay, there is also a tmp frequency equal to 1. Okay, so now I have to do, so this code is executed only once. So at the first, for the first word. But this code should be executed for other words. So how it should work? So first, I have to verify whether, so I have to execute the process which led me to insert element to 3. So look, so if I have a 3 and I'd like to insert a new element, I have to compare this element with a root and decide whether it is equal, smaller, or greater than. And depending on the result, I should go to left sub3 or to right sub3 or to increment the frequency counter. Yeah. So so how to do it? On okay. On CPP reference, we have help to function to which is called strcmp, so string compare. So look, this function is used to compare two strings, whether what is the relationship between them, and the return value is negative if value is before, so left argument is before the right one. Okay, so in alphabetic order, yeah. So 0 if they are equal, yeah? And positive if the right one is bigger than left one. So this function makes or solves our problem how to compare. So I can write a switch and in the switch so I get the word from the file, and let's assume that I have the node pointer, which is current, and the current is the root. So now I have switch and I have to string string compare, and I'd like to compare the first element, so the word, with current word. Okay. To use string compare, I have to use, okay, string H or C string. It doesn't matter, but we have to include this header. Okay, so let's assume that I'd like to create several cases. So case 0. So if this result is equal to 0, I have to, so it means that the current word, so the word in current node is equal to word I get from the text file. So it means that it was repeated. So it is enough to, okay, current frequency plus plus. Otherwise, so case -1, it means that so I hope it returns -1, but the documentation doesn't mention about this. It mentioned that it is negative value, but as far as I know, it should be -1. We check it. So if it is -1, I should go to the right subtree. So I should set the current to be equal to the current left, current L. And now this process should be repeated. Okay. Case 1, the current should be the current right, and the process should be repeated. Okay. So in this case, the process should be terminated. So it means that I found the proper element. Okay, so now, okay, it's only a scheme, so it doesn't work now, but I'd like to show you what are the possibilities. And now I'd like to refactorize this code a little bit. So look, let's assume that I have, so I'd like to move this code into the function. So now I create function find and insert. And here as the parameter, I pass a root. And I will pass a word. So to create this function, find, let's assume that it would be a void function, find and insert. I have node asterisk current and car asterisk word. So I have two arguments, current node and the word. And now I paste it. So I have switch word with current, if current frequency plus plus break, if -1, and here instead of current equal to L, I should call find and insert current left word. And again, find and insert current right word. Okay, but here we have certain problem because current left, this code is okay, provided that current left exists. If not, so let's look here, if we have only a single element, left and right are null pointers. So if I call the find and insert for root element and the word is different than current word, and I try to call this function for current left, and current left is null, my program failed. So here I have to add a condition if L is not equal to null pointer, and the same for this code if R, so right element, is not equal to null pointer. What shall I do else? Otherwise? Do you have any? So if R is equal to null pointer, so this condition is not true, it means that I get the leaf of the tree. So it means that I'm here at the leaf. So it means that there are no element, no next element. So how to solve this problem? I have to insert a new element. So let's add a function add node. So here I have current R is equal to add node, here word. The same I can do in this case, current left add node word. Okay. So how to implement add node function? The add node function has been already implemented. So look, the root is equal to add node word. Okay, so node asterisk add node char asterisk word, and here I have to paste the I have to paste this code, but instead of str temp word, I have to use str cpy word to temp word. So this function copies the character array of characters from one array into another one. So I allocate memory for a new node. I copy the array of characters. I initialize the frequency, and finally I initialize left and right subtrees. Okay. So find and insert, add node if there are no left subtree, and again for right subtree. Okay, so look, our code looks like this. I use add node for the first element or for further elements. I go to the other words, and starting from root, I try to find particular word in subtree. If it doesn't exist, I add this this node in a leaf. And if it is the end of file, I terminate this process. Okay. So if you run this code, it will create a binary search tree for this file. Now I'd like to print this element. So print 3. So I'd like to define function which prints all the nodes in the tree. So void print 3 node asterisk and now I showed you that to print 3 in alphabetic order, first we have to reach the most left element. So if node left is different than null pointer, call this function recursively. So print 3 for node left. Okay. So if the left subtree was printed, now I have to print myself. So cout okay, so now a single line is printed, so it consists of word, a separator, and the number of occurrences. And finally, I can print the right subtree. So all the elements in the right subtree are bigger than the current element. So they should be printed after it. Okay, so here I have the defined print 3 function, which looks like this. Okay, let's try to compile it. There are no errors. Okay, something was wrong. So let's try to debug it. Okay, so the word is red. So you can see that the license was red with and the ninth character is 0. So that's okay. Okay, so else. So the word all was taken. And now we go to find and insert. So let's go here. Okay, so switch case. Okay, so the problem is that the STL string compare returns 0, but it returns the negative value. It is not equal to -1. So in fact, I should write this function on another way. So if the string compare, or maybe int result, string compare, and now if the result is equal to 0, if the result is equal to 0, increase frequency. Else, if the result is smaller than 0, if the result is smaller than 0, so here I have to process the left subtree, and else if, oh, okay, it doesn't matter. So if I'm here, so if it's not equal to 0, if it is not smaller than 0, it means that it is greater than 0. So I can neglect the result greater than 0 condition. And finally, I have the code like this. Okay, so here. Okay, hope it works. Maybe this condition is not so, clear because we have a cascade of conditions, but it should be okay. Yeah? Okay, so let's run it again. Okay. Maybe we should, but it should be run faster, so something Okay, something was printed. So first I have to verify this function. So string compare. Probably I exchanged the arguments here. So string copy. So I have destination and source argument. So here in this function, the source argument should be the last one. So I copy the word into the node. Yeah. So that is the problem here. Okay. So now you can see that it works. So look, all words are ordered alphabetically. And we can see that next to every word there is a number of occurrences. So there, for example, was present more than 1,500 times. Of course, there is also possible to remove, for example, these elements. So I will have required and required merge point merged together. There are also elements which starts with capital letters. So I have to combine it also with lowercase. But you can tune it by your own. Now, hope you can see how to implement a binary search tree from scratch, and you can see that it takes less than 80 lines, so it's not so difficult to do it. Of course, in real programming, so when we try to write our own code, we use, for example, STL libraries like unordered map or map, and the STL map implements binary search tree. So we don't need to do it manually. But very important for me is you to understand how this structure works. And I think that to understand it, everyone should try to implement it by your own. Okay. Binary search tree is a first example of something which is called associative array. So what is the associative array? So in associative array, so in standard array, to address a particular element, we have to use an index. So it is an integer number, and if you want to select the 5th element from the array, you just write index 4. Yeah? If you want to select the 4th element, you need to use index 0. Look, if we have array, tree, that is a kind of also associative array because every node has a key. So key means, here it is called word, but key means that it is the element which organizes my array. So let me to find or to search a current particular node. So look, if I'd like to, for example, find the node with value word, it is enough to, to write this word and to go through the array, and we can find it. So for the tree, this element is called a key, and it led me to get access to particular element. This key is unique, so there are no way that two elements of the same key existed in array. So for example, we can imagine that if we have a tree object, like it works for map, for example, in STL. So in tree object, I can use a key like B. So it means that I'd like to find the element with key equal to B, and I'd like to print, for example, its value, so frequency. So this kind of dynamic data structure is called associative array. So there is a key and other elements which are treated as a value. Of course, it is not array as I showed you talking about standard array, because elements are not are stored in are separate in memory. Yeah, so they are not stored together. To find particular element, we have to perform several steps. But from the user perspective, the tree behaves the same like standard array. Remember that if we have balanced tree, so all levels are equally occupied, the number of comparisons, so the number of visits you have to perform is equal to log n. So if you have 1024 elements, at max you have to perform 10 comparisons. So it is less than for a list or for standard vector. Yeah? Okay, but now I'd like to tell you something about other types of associative arrays. So it is called a hash table. So what is the problem with binary tree? So if we have a key, which is a word, in every step, we have to compare a key with our word or the requested key. So in every step, you have to do it. So if we have 10 steps, we have to perform it 10 times. But look, comparing words is time consuming because I have to compare all elements in array. So the first character from requested key with the first character from the node key, and so on. So if the words are about 10 digits or 10 characters, and you have, for example, 10 or 100 steps to perform, you have to perform 100 times 10 comparisons. Yeah? So it's time consuming comparing to key which is a standard integer, because if we have integers, we can compare integer in a single processor cycle. Here we need much more cycles. So how we can cope with that? Here you have another form of associative array. It is called a hash table. So how hash table works? Look, I have a key which is a string key. So John Smith, for example, Lisa Smith, and so on. So for standard binary search tree, I have to go through all nodes in array in a tree, and I have, for every node, I have to compare character by character. Yeah? But here the concept is another. So look, if I have a key, I have to calculate something which is called a hash function. So here is an example how we can calculate hash function. So I take for example, the first character, and I add the second character and multiplying it by, let's say, a certain factor. The third. So you can imagine that I try to sum all characters up. If p is equal to 1, it is summing all characters up. And then I calculate modulo. So modulo limits the maximum value of this term, this expression. So look, if I why this mouse doesn't work? Okay. So if I look, let's assume that I have the word which consists of two characters, so A, B. I don't know what happened here. So I have to add the A plus B. Okay, I can multiply them, but look, what is the problem? If this factor is equal to 1, there are no difference whether I have A, B, or BI. If I have, different multipliers here, there is a difference between A, B, and BA. But you should see that the hash function doesn't guarantee that there are no two keys which has the same hash function value. But let's assume that we agree for this. So if we have the hash function value, it addresses a bucket. So I have standard array, the number of elements in this array is equal to q. So if I have modulo q at the end, the number of elements here should be equal to q. And then if I have a hash function, it addresses particular bucket. So in this case, using this key, I am able to get access to particular bucket or particular cell in a single step, like for standard array. So comparing to binary search tree, hash tables seems to be even faster. Because if I calculate hash function, I get a certain element in a single step. But what are the problems? Okay, here I can have duplicates because, for example, if John Smith and let's say P.Kaczmarek has the same hash function, they have to share the same bucket. Okay. What else? Okay. Calculating hash function is performed only once, but in fact, this is also time consuming. So if we have small binary search trees, it may work even faster than hash function. But for large sets, okay, the hash functions, hash tables are faster. What else? It doesn't matter how many elements we have, but we have to pre-allocate the array for q elements here. So let's assume that the q is equal 100. So it means that here I can have 100 unique keys, but I have to pre-allocate 100 elements. If the q is 1000, okay, I can have 1000 unique keys, but I have to pre-allocate memory for 1000 elements. Usually, the hash functions are larger than for 8 or 6, even 16 bits. So if I have 16 bits, it means that I have to allocate more than 65,000 elements. So so there are some benefits of this hash functions, but also drawbacks. By the way, if we talking about hash function, I'd like to mention what is the so you can meet a hash function also in different application, not only to hash table. So I'd like to tell you about passwords. So when you log in to a website or to IT system, you usually have to specify a password, but most systems doesn't allow you to recover password. So the system is not able to tell you what was your password, because this password is not stored literally. It is stored in a form of a hash. So for example, if your password has 8 characters or maybe 12 characters, it doesn't matter. For this password, a hash value is calculated. So an integer number is calculated. And then when you write this password again, for authentication purpose, your text password is converted into hash value, and this hash value is compared with the hash value in your client record. Yeah. So what are the benefits of this process? The first benefit is that even the hacker has the hash function, hash value, it can't do, or it's not so easy to recover the original password. Because look here, when I sum up all characters and calculate modulo q, it's not easy to say what was the original text here. So it's not easily convertible. So to log into your account, having a hash function value is not enough, because you have to write your password, and then the hash should be calculated. So if you have the hash value of your password, you can't log in. The most popular hash function for passwords is called MD5. But the problem is that if you use the standard password, so here you have the 10,000, the most commonly used passwords, and when you have a standard password, so, and when the hacker, you know, break the security barrier and get this MD5 values from user record, it can easily recover your password, because MD5 is like this. Of course, there are some other hacks like salt and pepper approaches in creating MD5, but okay, it's not time to tell about this. But you should be conscious that the passwords are stored in a form like this, and the same is for hash function. So if you have a hash table, your value looks like this. It's, you know, a number which address particular bucket here. So the only way to change your password, or the only way to recover your password, is to change it. If, for example, for some website, you can recover passwords and this website sends you this password, you know, in a plain text, it means that in database, this password is stored also in a plain text. So it's very, so that there is a high security risk when internet providers or other website admins store passwords not in hash form. Okay, but there is another risk that, look, because here I have only a value, there are no guarantee that for my password there exists another string of characters which lets me to get to my account. So of course, if we have eight characters, it's almost impossible to, you know, to have or to guess another set of characters which let me to get log in, but in theory it is possible, yeah? That instead of, so this MD5 is generated by 1, 2, 3, 4, 5, 6, but there can be another set of characters which let me to, which has the same MD5. So in this case, I can log in to my account using this set of characters and using another set of characters as well. Okay. What about duplicates? So it is a real problem that if we have, let's say, 200 buckets in hash table, there will be duplicates because it's enough to have more than 200 elements. So if you have more elements than buckets, always the duplicates will be observed. So how to do it? So if there are two keys with the same hash value, I can, for example, organize the bucket in a form of list. So when I have a bucket, it doesn't mean that I reach my element. I can compare these elements, you know, exactly. So I can compare whether this name is exactly equal to the name of the key. But look, the number of comparison here is smaller. So here it's enough to perform, let's say, 2 or 3 comparisons at max. So in this case, I have hash array mixed with, let's say, a list. And this is very commonly used way of storing data. In STL, we will be talking about STL. In STL, we have a container which is called unordered map multi, and this is hash table with possibility of storing more than single value in a bucket. Okay, here you have another dynamic data structure, which is called a heap. I don't want to spend a lot of time to explain how it works and how to create a heap, but I'd like you to know a general rule about it. So a heap, in fact, is binary search tree, but all elements are stored in an array. So I have continuous block of memory, and I store these elements in a continuous block. So there are no separate nodes. But every index, so when I have a tree of height, let's say 1, 2, 3, 4 levels of nodes, I am able to exactly determine the index of particular node. So the first node is a root. The second and third nodes are the left and right node of the first level. Yeah? The 4, 5, 6, 7 are also the nodes of the third levels. So I am able to, exactly reach every node in a single pass. But of course, if you want to add a new element to the heap, you have to reorganize many elements. So there is a process which led me to insert elements, but it consists on moving elements. Yeah, but okay, it's not the topic for this week. Okay, so that's all for the topic of dynamic data structure. And now I'd like to tell you something about a standard template library. So the library which led us to use this dynamic data structure in real programming. Because now, on the previous lecture, I told you, about the theory of dynamic data structures. But now I'd like to show you how we can use this theory in practice. Okay. This presentation was adapted from presentation of Brain Strostrup. It is guru of STL and C++. So it is a guy who creates a standard for C++, and I think one of the most prominent men in this community. Before I start talking about applications, I'd like to present you a general idea, or maybe some key elements and logic of standard template library. So first, I'd like to tell you something about generic programming. So far, your programs are not generic, they are concrete, so something which is called a concrete programming. So let's say, so let's start from what is generic programming. So in case of generic programming, I mean that generic programming is somehow separated from data organization. So first we have data. They can be organized on, different ways. Let's say they can be organized in a form of list, of tree, of array, of hash array, whatever. But for all of them, we can apply some algorithms, which, for example, are looking for elements or sorting this container and so on. And the idea is to create a single algorithm, so let's say single function, which can be applied for all of these data structures. So not only data structures, but also data types. So look, the idea is to create something which is universal. And if we have, for example, concrete programming, let's try to create a new So let's assume that I have a float array. And when I'd like to write function which fills all elements with of this array, I have void fill float array okay, and int n, so the number of elements. So to fill of these elements, I need for int I equals 0, I smaller than a, and I plus plus, and here array index I equal to value. So to fill these elements, I call fill array value, let's say 1, number of elements 100. But try to imagine that I need array of doubles. So to call this function for array of double doesn't work because the arguments are like that they fit only to floats. So I have to overload this function and create another version of function for doubles. So look, the only difference is that the type, the argument type is different here. So in concrete programming, we have separate function for every data type and for every container. So if we have a list of floats, I have to create different function for processing list. Even this function does the same. So it fills all elements with with value. Yeah? So in generic programming, the goal is to create a single function which is able to handle different types, different containers. And this logic or paradigm is implemented in something which is called STL, Standard Template Library. The Standard Template Library is a part of C++, so you don't need to install a new library or to download something. It is embedded. Standard template library consists of several, blocks. I will tell you what are these blocks, but there are algorithms which let me to operate on different data types and different dynamic structure on the unified way. So I don't need to perform special treatment for, let's say, array and another treatment for vector, for tree or hash table, etc. So you can see that it is it works quite good. What's more, it is optimized for disk access, for memory consumption, for time performance, and so on. So even if you create your own, let's say, binary search tree, probably the algorithm which is implemented in STL will work faster or at least the same as yours. So look, here we have concrete algorithms. I showed you the concrete algorithm for different types, but here you have concrete algorithm for different data containers. So first, we have the container in a form of array. So I pass this argument, and the goal is to sum all elements up together. Yeah? So here I have array, the number of elements, and I sum them up, and finally return the result. If my array, or not array, my container is organized in a form of list, unidirectional list, I have to pass the pointer to the root element. And now the same algorithm looks different because I have to perform it as long as I get the last element on a list. And here I have to get access to data field. But look, if we try to analyze this code, we can find several similarities. So the similarities are first, here, even we have different types, we have the variable which is initialized with a neutral value. Here I have a duration condition. This condition is different for list and for array, but it exists in a term of that I need something like this. And here I have the go to the next element. So I have the code which moves to the next element. And finally, I have the operation I have to perform. So here I have the operation of summing elements. Here, the value of I is the value of current element. In this case, first selector data is the value of the current element. So depending on data structure, different way of this action has to be, so different actions has to be performed. But look, oh, sorry. So we will continue this topic tomorrow. So sorry for 5 minutes that this lecture was 5 minutes longer. Okay, so tomorrow we will continue this topic. Yes, tomorrow you have a test. Tomorrow we have only a single lecture, so at 9:45. But 5 minutes or 10 minutes before the end, we make a short quiz. This quiz will be not about STL because we have, okay, maybe tomorrow I will tell you something more about STL, but it will be mostly focused on dynamic data structure. Okay. So thank you for your attention and goodbye. Sure.